Imagine you come home on a cold winter day, take off the gloves and turn on the heating. You heat with oil and feel a little bad about it, but we've got used to that worry. So here's something new to worry about. What happens with the heat itself? Doesn't that also, well, heat up the planet? It does, and it will become a problem eventually. If that's true, then why doesn't anyone ever mention this? Can't we just build an air condition for the planet? We can, in principle, and that's what we'll talk about today. You've probably noticed that your phone gets warm when you use it. I hate to break the news to you, but it's not because it likes you so much. It's because it's doing a lot of calculations. Those require energy. The heat is a byproduct of using energy. That's why phones get warm, it's why lamps get warm, car engines get warm, and it's also why power plants of all types get warm. They all emit heat into the environment, and eventually all that heat warms up the planet, in addition to the heating that we get from greenhouse gases. The reason for this is, once again, physics. When we colloquially talk about energy, we mean the stuff that comes out of a battery or that we get out of fuel or out of a power outlet. Physicists call this more specifically free energy. That it's free doesn't mean it insists on taking guns on a trip to the mall. It means it's useful energy, energy that you can do something with, like making a phone call or driving down the road. You don't just need energy for that, you need free energy. The other energy, the energy that you can't do anything with, is called heat, or sometimes more specifically, waste heat. How can energy possibly not be useful? Well, for example, while you're watching this video, there are lots of air molecules bumping off your head. These air molecules move, so they have a type of energy called kinetic energy. The average kinetic energy of the air molecules is the air temperature. There's a lot of energy in the air around you, unless your room temperature is at absolute zero, in which case physics would like to have a word with you. But if there's so much energy in the air, why can't your phone just recharge from that? Because the air molecules are randomly buzzing around. They are very disordered. They have high entropy. And something that has a high entropy doesn't change any further. It stays on average the same. You can't extract energy from the air because that would require reducing the entropy of the air. So almost all the energy that's in the air is heat, and basically none of it is free energy. Free energy, loosely speaking, is the counterweight to entropy. If you want free energy, you need something with low entropy. If you want to bring down entropy, you need free energy. If you had air that was somehow ordered and therefore had smaller entropy, then you could do something with it. It would contain free energy. That could be, for example, because the temperature in one part of the room was lower than that in another part. If that was so, then you could indeed extract energy from that. That's what a thermoelectric generator does. Now, when we colloquially talk about sources of energy or renewable energy, then we usually mean sources of free energy. There are many different types of free energy. For example, chemical energy, like that in fossil fuels, or nuclear energy, that's in atomic nuclei, or electromagnetic energy, that's in solar radiation. We use this type of energy by converting it into something else, often multiple times. For example, you may burn coal and convert the energy into electricity, which you then use to run a fridge. The issue is now this. Each time you convert one type of free energy into another, something of it gets lost into heat. It's kind of like currency conversion. If you convert euro to US dollars to British pounds to yen, eventually nothing's left. In a similar way, if you convert energy from nuclear to thermal to chemical to electrical to mechanical, eventually nothing's left. You must either store the energy again in some other form, or it's emitted as waste heat. This means the more energy we use, the more we heat up the environment. And this is a different cause of global warming than the increase of carbon dioxide levels. How big is the effect of this waste heat? A few months ago, Thomas Murphy from the University of California, San Diego, published a comment in the journal Nature Physics in which he crunched the numbers. It roughly works like this. We know how much energy comes in from the sun to the surface of Earth. The energy which comes from the sun is free energy. It's useful. Plants can use it to grow, and we can use it to power lawnmowers, to cut down the plants, which is okay because physics isn't concerned with the meaning of life. Actually, we're not interested in the energy, we're interested in the energy per time. Energy in and by itself doesn't tell you much. If someone tells you they have an income of 100 euro, it makes a difference whether that's 100 euro per hour or per year. And energy is like that. We want to know how much comes in per time. Energy per time is called power. We currently don't use most of the power that comes from the sun. It's absorbed by the surface of Earth and re-emitted as radiation in the infrared. It heats up the atmosphere from the surface up and eventually escapes back out into space. I talked about this in more detail in a recent video. The temperature on Earth remains the same so long as the total power in is the same as the total power out. But because we're increasing carbon dioxide in the atmosphere, less goes out than it used to, which is why the surface temperature is rising. It'll continue to rise until the power that comes in equals the power that goes out again. The difference between the power that goes in and that goes out is called the forcing. But this isn't all. We're also adding to the energy that's emitted on the surface because all our power plants emit this waste heat. And that waste heat now also must get out. This means that the temperature on Earth will increase more than just from the greenhouse gases because the difference between in and out just got larger. The forcing increased. Murphy calculates that at present, the contribution to the forcing from the waste heat is about 1 order of magnitude smaller than that from the greenhouse gases. So at the moment, it doesn't make a big difference. But in the past centuries, our collective energy consumption has increased almost exponentially. And the waste heat increases exponentially with that. Exponential increases have this weird property that they sneak up at you from behind. They look like nothing for a long time and then suddenly they blow up and overtake everything. The same is going to happen with waste heat. If we go on to exponentially increase our waste heat output, the result would be disastrous. Murphy calculates that in 400 years of time, the surface temperature of Earth would reach the boiling point of water. That'd be unpleasant. Now, it's unlikely it'd get that far because we'd all die before that, which ought to slow down the economy a little. And I want to be clear that this is not something we need to worry about at the moment. At the moment, the carbon dioxide is the issue, not the waste heat. But waste heat is a problem that we'll have to find a solution for sooner or later. At the moment, we do, in fact, waste most of the free energy that we use. According to an estimate from a group of German researchers, we currently use only 28% of it. The rest is lost into the environment. So what can we do? To begin with, what the waste heat does depends on where the energy comes from. This is because the energy that comes from the sun is what's giving rise to the current temperature already. If we make better use of sunlight, this isn't going to increase waste heat because it's there anyway. Another way to say this is that the power from the sun is already included in the forcing that's responsible for the temperature increase. When we use solar energy, all we do is delay the time it takes for the incoming sunlight to turn into heat. This isn't only the case for direct solar energy, it's also the case for all energy derived from solar energy, such as biofuel and wind. Yes, wind is mostly caused by solar energy. Sunlight heats the air more near the equator than near the poles, which, combined with the rotation of Earth, causes most of the big wind patterns. And hydropower partly comes from the pull of the moon, but mostly from precipitation that's again driven by sunlight. All this energy is in the system already and is creating waste heat anyway, so if we make use of it, that won't boil the planet. For the same reason, however, the amount of energy we can extract from those sources is limited. We are currently nowhere near those limits, but eventually we'd have to find other sources of energy. That leaves fossil fuels, hopefully with carbon capture, nuclear fission and fusion, and geothermal energy. All of these will release extra waste heat that contributes to warming. To deal with this, for starters, we can reduce the amount of waste heat that is produced by power plants. If you remember what I told you about entropy, air that is warmed up by a power plant in one particular place hasn't yet reached maximal entropy. It'll only reach maximal entropy once the warm air has diffused into the environment. This means you can extract more energy out of power plants than we currently do in almost all cases. Another way to put this is that what engineers call the waste heat of a power plant is not already waste heat on a global scale. The most obvious way to use waste heat from power plants is to use it directly for heating. This is done in some places already. Prague, for example, heats over 250,000 households with waste heat from a coal power plant. The Russians are doing the same thing in a town near the Gulf of Finland with waste heat from a nuclear power plant. This is a rather obvious thing to do that makes sense both environmentally and commercially, and I expect that in the future it'll be done more often. There are other facilities besides power plants whose waste energy can still be put to use. For example, the Danish city of Aalborg provides about 24 households with waste heat from a crematorium, the probably only fat-burning exercise that actually works. In Cologne, Germany, several schools use waste heat from sewage water, and the Islington district in London captures waste heat from the London Underground. Big data is a particularly great source for hot air, and that too is used in increasingly more places. For example, a Facebook data center in Denmark donates its waste heat to a local hospital and other buildings in the area. An Amazon data center in Ireland heats parts of Dublin. Indeed, the Norwegian government now requires that data centers make use of their surplus heat, and I expect that other countries will soon pass similar regulations. These are all examples for how energy can be used more efficiently, so that less of it goes directly to waste. But again, there are limits to what you can do this way. This will slow down the increase of waste heat from energy consumption, but eventually it's not going to solve the problem. So what else can we do? We can try to reduce warming the same way that people try to reduce warming caused by carbon dioxide. The most obvious way is to take carbon dioxide out of the air, which will cool the planet. But since plants need carbon dioxide, this too would ultimately not solve the problem. Another option is to reduce the amount of power that comes from the sun. People have put forward a number of fancy ideas for that, such as putting huge mirrors between the Earth and the sun. For example, in 1989, James Early proposed to put a mirror near the first Lagrange point. The first Lagrange point is about 1 million miles away from Earth. It's a place where the gravitational pull of Earth and the Sun almost cancel out, so spacecraft positioned there stay largely put. Early suggests that we put a reflective disk at this Lagrange point. He calculates that to block 2% of the incoming radiation, the disk would need to have a diameter of about 2,000 kilometers. He estimates that even if the disk was as thin as 10 micrometers, it'd still weigh 10 to the 8 tons. Inflation adjusted, it'd cost about $20 trillion. He also says that the shield could be built on the moon, which will happen around the same time that pigs learn to fly. There are a bunch of similar ideas. For example, putting a ring of large space reflectors around our planet and so on. We'd need about 55,000 of them, each about 100 square kilometers large, in low Earth orbit. We could instead use spacecraft with only 1 square kilometer size, but then we'd need 5 million of them. These are all ideas that might be physically possible, but they are not economically possible. An option that's economically possible is to inject reflective substances in the upper atmosphere. This is known as stratospheric aerosol injection. This would bring down the incoming solar radiation, but have several downsides. For one, it isn't any good to combat carbon dioxide increase because the carbon dioxide would still be there. It could significantly change precipitation patterns, which would be devastating for food supply. And carbon dioxide doesn't just warm up the planet, it also causes ocean acidification. Besides, if you're concerned with the issue of waste heat, blocking sunlight doesn't make a lot of sense because it just means that there's less solar power for us to use. You just replace the power coming in from the sun with power generated by other means. And what's the point in that? No, if you want to solve the problem of waste heat, you need to get heat out of the atmosphere, not prevent it from coming in. So how do we get heat out? One way to do this is to make it easier for the heat to escape by removing clouds that trap it. It's a particular type of cloud which does that, the so-called cirrus cloud. These clouds are thin and wispy, float at high altitudes, and are typically made of small ice crystals. Some researchers have proposed that we could spray those clouds with substances that promote the growth of the ice crystals until they fall down. This is known as cirrus cloud thinning and would make it easier for heat to escape from the surface of Earth. But no one has any idea if it would work or how efficient it would be. Another way to make it easier for heat to escape is to convert it into radiation that isn't affected by the atmosphere. If you remember, incoming sunlight mostly makes it to the surface of the Earth because the atmosphere is transparent to electromagnetic radiation with wavelength in the visible range. But this isn't the only wavelength range that the atmosphere is transparent to. It's also mostly transparent to wavelength in the range 8 to 13 micrometers, which is in the infrared. In this range, neither carbon dioxide nor water vapor absorbs much, so the radiation goes out into space almost undisturbed. We can therefore, in principle, take that waste heat which we're generating and make sure it's emitted mostly in this range where the atmosphere is transparent, which is also called an atmospheric window. For this to work, we need to design metamaterials with just the right properties. That this is possible was demonstrated a few years ago by a group of researchers from Canada. They designed a metamaterial which does just that. It's very reflective for incoming sunlight, and if it gets heated from the air around it, it emits mostly in the atmospheric window. I know this sounds odd, but this means that the material cools itself. They have shown that, when exposed to sunlight, it stays 5 degrees below the ambient temperature. These researchers have also created a startup company called SkyCool, which has sold panels of the material to several stores. They've seen significant energy savings because they need less air conditioning. I talked more about what metamaterials are good for in an earlier video. Again, though, there's only so much this'll do because we can't feasibly cover the entire planet with those panels, which is why people have come up with more ambitious proposals to get the heat out of the atmosphere that are basically planetary-sized air conditioning units. One idea is a giant heat circulation that channels warm air from the surface into the upper atmosphere. This could be done by huge chimneys that would have to be at least 5 kilometers in height and about 1 kilometer in diameter. The inventor of this method, Michael Pesoczynski, has estimated that just 10 of these super chimneys would be enough to offset the heat surplus that causes current global warming. He has patented the idea and built a prototype that is about 2 meters high, so all we now have to do is to make these things 3,000 times taller. Some have suggested that one could use a floating fabric instead of a solid material for the chimney. Another proposal is a balloon factory. One blows hot air from the surface into huge balloons and then sends them up into the atmosphere. And some researchers have pointed out that since tornadoes are basically chimneys that transport heat from the surface to higher altitudes, maybe one could just create artificial tornadoes to improve surface cooling. What could possibly go wrong? A related proposal does basically the opposite. Instead of blasting hot air up, one pulls cool air down. The reason all these ideas work in principle is that free energy makes it possible to reduce entropy. This means we can use part of the free energy that we have to reduce the heat in the atmosphere by pumping it into outer space. There's nothing in the laws of physics that forbids this. And yes, all these cooling systems would also combat global warming. But to say the hopefully obvious, we're not going to build them anytime soon. Like putting huge mirrors into space, the problem isn't that it's physically impossible, but that it's economically impossible, at least at the moment. But if we play our cards wisely and manage to not go extinct in the next 100 years, then we'll sooner or later have to build an air condition for the planet. It's either that or use less energy, and then we'll never get those flying cars. So, in summary, power plants create waste heat, and that waste heat adds to global warming. At the moment, it's a small contribution, but the more energy we use, the larger the contribution will become. Researchers estimate that in a few hundred years, it could become a problem. To prevent that from happening, we can make power plants more efficient and use more solar and wind energy. Beyond that, we would one day have to build a giant air conditioning system to cool the planet, if we survive that long. As we've just seen, solar power is different from other energy sources because we've been getting it all along anyway. We just need to make use of it. But how do solar panels work? What's the physics behind them? There's a great course about this on Brilliant, who have been sponsoring this video. Brilliant has courses on a large variety of topics in science and mathematics. It's a fresh and new method of learning with interactive visualizations that really give you a feeling for how things fit together. In their course on solar energy, you learn what light we get from the sun, what properties it has, and how we can make use of it with certain materials. It really makes it sink in how much potential there is in sunlight that we're barely using. But maybe you're more interested in quantum mechanics. In this case, let me mention that I work together with Brilliant on a course that accompanies my videos on quantum mechanics. This course will introduce you to quantum mechanics starting from the very basics, so you don't need to be an expert already to understand it. It's an introduction to interference, superpositions and entanglement, the uncertainty principle, and Bell's theorem. And like all their courses, it comes with interactive graphics and follow-up questions. If you're interested in trying Brilliant out, use our link brilliant.org/Sabine and sign up for free. You'd get to try out everything Brilliant has to offer for 30 days, and the first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.